Hi everyone, my name is Mengxi, and today I would like to talk about how we can learn human preferences from a sequence of physical corrections. A common paradigm of human-robot interaction is when humans and robots take turns to manipulate objects in a dyadic fashion or in an assistive settings, where a user might use a joystick to teleoperate a robot. However, these two common paradigms are not physical. We refer to physical human-robot interaction when a human physically makes contact with the robot as a way of providing corrections or feedback. For example, physically moving a robot arm to guide its behavior. Well, why are these physical human-robot interactions useful? Let's take a look at an example. Here, the two robot arms are carrying a grocery bag to the table. The robot plans to carry the bag to the blue region, while in fact, the human have more goals in mind. The user wants to place the bag on the green region while also trying to hold the bag upright without squeezing or stretching it. Since the robot does not know the human's intent, it goes to the incorrect blue region on the right. A human can provide physical corrections, which are often very easy and intuitive, and intervene to push the robot towards the left side. These physical interactions, as in an example we just saw, are usually intentional and informative. So our research question here is, how can we interpret them to learn human preferences and objectives? One classic category of PHRI strategy is simply treating the physical interaction as disturbance. To make the robot compliant, these types of work will modify the trajectory, but only in the direction of the human correction. Here, the robot only treats the human's interactions as local information and adjusts nearby waypoints accordingly. Let's look at an example. Here in the video, when the human pushes the robot down, the robot is compliant and goes down. But when the human lets it go, it returns to its original trajectory, and thus the human has to intervene several times. These types of methods include impedance control and some extensions of them. Another category of methods instead try to learn important aspects of the task from PHRI and then replan. In this way, the robot would relay the human's low-level torque input to high-level trajectory parameters. As shown in the video, the human intervenes less compared to the impedance control method because it learns from these interactions and replan. But previous work only assumes that human corrections are greedy and they reason over these corrections independently. So what is missing in greedy corrections and independent reasoning? Well, let's return to our grocery example. Again, two robot arms plan to carry the bag to the blue region, while the user wants to place the bag on the green region and hold the bag upright without squeezing or stretching it. Observing the robot executing an unwanted plan, the human will intervene. Now it has two possible choices. If it moves the right arm first, the bag will be squeezed. If it moves the left arm first, the bag will be stretched. Either way, if we just greedily reason over this single action, the robot will think that it's okay to deform the bag. However, this is not what the human intended. So our key insight is that human corrections are not independent events. In fact, we often use multiple correlated interactions to correct the robot. Let's now jump into the formulation. We assume human reward is represented by an underlying function R that is a linear combination of the features phi of the trajectory psi. The linear weight is denoted by theta. However, this data is not always known by the robot. With that being said, the robot will maximize the reward with its best estimate of data, which is theta 0, to get its planned trajectory psi r0. Before diving into how we model human corrections, let's walk through a simple example for how humans provide corrections. Imagine you have a robot arm in your kitchen helping you with sorting your groceries. It's now putting an apple to the plate on the top shelf. Normally, the task is easy. The robot just follows a straight line to the upper shelf. However, today, you have friends coming over, it's kind of a busy day, dinner is served already, and the blue plate is misplaced to the bottom shelf. Ideally, in a user's mind, you would want the robot to move away from the dinner plate and put the apple on the blue plate on the bottom shelf. However, without all of this information, the robot would just go with its normal plan, which is following a straight line. Seeing that it's gonna hit the dinner plate, the human comes in for her first intervention, AH1. She pushes up the arm so that the robot moves up. Now that we have the human corrections AH1, we're gonna smoothly deform the robot's original trajectory in the direction of the human correction AH. Here, mu and a are hyperparameters controlling how conservative this deformation should be. With this propagation, we now have a potential intended trajectory, SH1, that the robot can follow. We then proceed with this trajectory until the human sees that the robot going towards the incorrect upper shelf and decides to intervene again. We propagate this second intervention the same way as we did for the first one, and then get a trajectory SH2. And if there are further more corrections, we repeat the same propagation for all of them. We then proceed with the newly propagated trajectory SH2 until the task is finished. Now, returning to our formulation, we have the reward defined. We have initial robot trajectory based on its best guess of the reward parameter. This guess might not be accurate, so that along the execution, the human might provide sequences of corrections, AH1, AH2, etc. We denote the set of all human corrections to be capital A of H. These human actions provide observations about the reward parameter theta, and thus our observation model is probability of these corrections given the initial robot trajectory and the current estimate of the reward parameters. Let's take a closer look at the observation model. In the observation model, we have the original robot trajectory psi r and theta. Now we observe a sequence of human corrections, AH1, AH2, and we want to understand how these actions convey information about the parameters theta. Looking back at our example of providing corrections, a more intuitive way thinking about these corrections is in the trajectory space. Since we can connect the actions with the propagated trajectories, and then evaluating how good the trajectories are becomes directly related to theta. So that's exactly what we do. Formally, we have these corrections AH that tells us when and what corrections the human provides. We then propagate each correction to an intended trajectory. For example, in the grocery bag scenario, the user provides 4 corrections corresponding to the 4 trajectories here to guide the robot to place the grocery bag on the green region while avoiding any stretching or squeezing of the bag. Now, remember, our goal here is to find a new estimate of theta based on the sequence of corrections. Applying Bayes' rules tells us that this estimate of theta depends on our prior and our observation model. We then replace the original observation model with the one in trajectory space. Okay, now let's go over how we learn from the sequences. On the left, this is our ultimate goal. We want to find the human preferred theta given human corrections. And on the right, we apply Bayes' rules. The highlighted observation model in trajectory space is missing, and we're going to talk about how we model that. We start by introducing the auxiliary reward function d of psi h1 to psi hk and theta. We refer to d as the accumulated evidence of a sequence of preferred trajectories psi h1 to psi hk under reward parameter theta. The accumulated evidence contains 2 parts. The first part captures the sum of trajectory rewards. The second part is related to minimum human effort. Alpha and gamma are 2 hyperparameters decaying the importance of previous corrections and determining the relative trade-off between intermediate reward and human effort respectively. And then we model humans as noisily rational agents whose corrections maximize accumulated evidence for their preferred theta. Now, when we plug in everything, we get this equation. Since the partition function in the denominator is intractable, using Laplace method, we approximate the normalizing factor with the maximum value. Now, everything is good. We just need to solve the optimization, and that gives us the observation model, which allows us to find new estimates of data based on the sequence of corrections. We use the grocery bag example as our main robot experiment, where 2 robot arms are carrying a grocery bag to the table. The robot plans to carry the bag to the blue region, while in fact, the human has more goals in mind. The user wants to place the bag on the green region while also holding the bag upright without squeezing or stretching it. Not knowing what the user truly wants, the robot starts off with an initial trajectory going to the blue region in the right, as outlined in the video. We start from psi R0. With humans sequentially providing corrections, we get from psi H1 to psi H4. To evaluate the effectiveness of our method, we conduct experiments with some users. Here, we show the likelihood of 3 different reward parameters over time. The darker red and blue denotes the human preferred reward, while the lighter colors show other non-preferred reward parameters. We can see here, our sequence model successfully infers the reward while the independent baseline fails. We also experiment with 9 users. Here, we show our overall performance over 9 users. The darkest color corresponds to the actual human preferred reward, while 2 other light colors refer to incorrect human reward. Over 9 users, the independent baseline cannot discover human preferred reward with sequences of corrections, while our method can successfully infer human preferences. We also demonstrate our individual user results. As it can be seen, our framework outperforms consistently over the independent baseline for all users. In summary, our task is reward inference from human corrections. The human has preferences but unknown to the robot, and the robot tries to figure it out through human corrections. Instead of reasoning over each correction independently, we argue that human corrections are correlated, and we reason over these corrections together by propagating them to a series of intended trajectories. Our method achieves higher accuracy compared to independent baselines consistently across all of the users. Thank you for listening.